Hello everyone, my name is Priyanshu and today I will be explaining Quicksort. So Quicksort is basically a divide and conquer algorithm sorting technique which uses divide and conquer method. Okay, I will explain you how. So we have taken an array this. Okay, so we have to sort it. So the main core logic you will understand after I explain you with a real world example. Suppose you are in a library and you are asked to arrange books in a shelf. Okay, so the main core logic of doing quick sort is to just pick one book and place in its correct position such that all the smaller number books are at the left and all the larger or greater number books are at the right. Then you can see the book you have in your hand or placed anywhere, then it will be at its correct position. Now you are just left with the left pile of books and right pile of books. Do the same, perform the same, then your shelf will be sorted. So we will do something similar. What we will do, the main core logic of this quick sort is pick a pivot element and place in its correct position. Pick the pivot element and place in its correct position such that all the elements less than or equal to the element pivot element is at the left and all the elements greater than the pivot element are at the right. So we have chosen, we can choose any pivot element, but here we are choosing the first element as our pivot. Now we have chosen 7. So what we will do, we will place 7 at its correct position. So we can see we have placed 7 at its correct position such that our all the elements which are less than or equal to the pivot element are at the left and all the elements greater than the pivot element are at the right. We can clearly see in this array. Now what we will do, we have to perform the same quick sort in the two arrays which we have got. So we will divide it into two from, we can say, from 2 6 1 5 7 one part, and the second part is the right 10 9 15. So we will consider them as individual arrays. Now we will perform the same quicksort in both the arrays. Similarly, the first we will choose first as our pivot and we will place 2 as at its correct position. Then again it will be divided into 2. Then we will stop when only one element is left. So we can say, we can see one only there is one element, so it's already at its correct position. And the right side 6 5 7, we will again perform the quick sort. 6 will be at its correct position, and then perform the same in 5 and 7. 5 and 7 are one size array, so they are already at its correct position. And similarly this side 10 and 15, 10 we will place at its correct position, and then 9 and 15 also are one size array, so they are already. So this way, placing the pivot at its correct position and dividing the array into two parts, from the starting to the pivot minus 1 and from pivot plus 1 index to the last, we will perform the same quick sort. So that's why it's called divide and conquer. So we will do this in place. I mean, we will not use any temporary array, we will just sort in place. So it's also an in place algorithm. Okay, so now you must be thinking that how we will place the pivot at its correct position. For this we will use two pointer techniques. We will use array and pointer, a pointer I, which will be at the first I mean the first index, and j pointer will be at its last. So we can see in the array I will be equal to 0 and j will be equal to the size of the array minus 1 index. So I will be at 7 and j will be also at here at the last 7. Okay, so what is our goal? Our goal is to place all the smaller elements, smaller and equal to elements to the left side of the pivot and greater elements to the right side of the pivot. Okay, so we will keep incrementing I unless and until we find an element which is breaking the rule, and we will similarly keep decrementing j unless and until we find an index of j which is breaking the rule. And just when we will find I and j, we will check if I hasn't crossed j, we will swap I and j. Okay, and at last what we will do, if I and j has crossed, okay, so we will see that j will be in the region of the first part of the array. Okay, so in the first part of the array it will be at the last index. Okay, so at that time when I and j will cross each other, this is the perfect time to place or swap pivot with the jth index element. Okay, so by doing swapping we will see that our pivot will be at its correct position. Okay, so this way we will place pivot at its correct position, and this is the algorithm of Quicksort. Now I will go through the implementation part. For implementing I am using the GFG portal. Here we can see this is the two functions are given, Quicksort and one function for partition. So in Quicksort, what I said, first of all, what we have to do is to know about the partition index. So we will create a variable partition index. What this variable will do, I am telling you, it will go to the partition function, and partition function will do two things. First thing is to place the pivot at its correct position, and second thing, return the position of the pivot elements such that we can again perform quicksort in the two divided arrays, left and right. So we will call the partition function. So we will pass array and the starting index and the last index, low and high. Now we will ask him again to perform quicksort to this array from low to the partition index -1. This will be the first half of the array and first part of the array. Okay, now again we will do perform quicksort to the next part of the array. This will be from partition index +1 to the high, and this way our quicksort function of 4-line codes is ready. Now we have to just code partition function. Partition function what it was doing, just placing the pivot at its correct position and returning the partition index, the pivot index, after finally placing the pivot at its correct position. So what we have to do, we have to place the pivot at its correct position. So let's take a pivot. So let's our pivot be the first element. So what will be the first? This will be array of low. Okay, now we have to use two pointers. So let's say I is the starting and j will be the ending. Okay, now while I is less than j, what we have to do, we have to just keep incrementing I until the condition is broken. What was the condition? That array of I is less than equal to pivot. Okay, and we have to make sure uh, of the edge case that I we are incrementing I, and I should not exceed the last index. Okay, because we are doing I plus plus. And similarly we will decrement j also until the condition is broken. If we find any element greater than the pivot, we have to just decrement I, and we have to make sure about the edge case. J, I mean I should be less than equal to I minus 1, and j should be greater than equal to low plus 1. Low plus 1 because we are decreasing j. Okay, and at last we will check if I is less than j. If it hasn't crossed j, we will just swap I and j index elements. Okay, so now if we see I has crossed j, now we will just swap our pivot element that will be at array of that will be at low index. See, pivot is equals to array of low, it will be at low index, and we will swap it with array of j, because j now will be at the region of the first array and at the last index. So where we will place the pivot, so we will just swap the pivot with j index element. Okay, now what we will do, the first task of this partition function is done, to place the pivot at its correct position. Now we have to return the pivot index, so we will simply return the pivot index will be at j, so we will simply return j. Okay, so the function is complete. Now let's compile and run it, and let's see what happens. Okay, so it's giving runtime error. Let's see what's happening here. So partition index, okay, we have declared correctly. Okay, Quicksort is also correctly declared, spelling is also correct. Partition index plus 1 up to the high. Okay, so the problem is we are not handling the base case, so we are using recursion, so we have to handle a base case. So we will check if there is only one element left in the array, so we don't have to do anything, we have to just return from there, because the one size array is already sorted and it's already placed in its correct position. So this way, if we compile it after handling the base case of the recursion, uh, it's compiled and submitted. Let's check whether we are able to pass all the test cases or not. Okay, so we are able to pass all the test cases. Now I will tell you about the time and space complexity. So we can see that we are using recursion also, and we are using two functions. So this quicksort function is a recursion function, so it will use some stack space. Okay, so what do you think, how many times we will divide it until we find, we will divide array into two parts, and we will divide until the size of the array is 1. Okay, so this way uh, it will go log n times. Okay, and this partition function is just taking O of n time, big O of n time, because uh, no element is checked, or the pointers are going on the element such that no element is iterated two times. Okay, we are just uh, going on an element just not more than two times. So you can see that we are incrementing j and incrementing I and decrementing j. So its time complexity is only big O of n. So log n times here and O of n here. So the total time complexity will be big O of n log n, and the stack space, the recursion space which we are using, it will be uh, log n, big O of log n space, because how many times the recursion is going until we reach the base case. So the recursion stack space is creating taking log n space. Okay, now if I tell you more thing about this quick sort, it's the time complexity and space complexity is totally dependent on two things: the array, how the elements are arranged, whether they are arranged in a sorted order, whether they are arranged in a reversely sorted order, or randomly arranged. And the second thing is the pivot, which element we are choosing as our pivot, the first element, the last element, the median, or the element, a random element. So it's totally dependent on the array and totally dependent on the pivot we are choosing. So we can read in the GFG article here that the best case and average case time complexity is big O of n log n, and worst case is O of n square. Because big O of n log n, because if a balanced recursion takes place, and big O of n square when an unbalanced recursion takes place. Okay, and if we talk about the space complexity, the best case and average case space complexity is big O of log n, because the recursion is taking log n space. Okay, recursion stack is taking big O of log n space, and in the worst case it will be big O of n. So this is also due to the balanced recursion and unbalanced recursion. Okay, so this is the time and space complexity of it. And if I tell you one thing more about it, it's an unstable sorting algorithm, because it does not maintain the relative order of the elements. Okay, so this is all about quick sort. Thank you.